Hello and thank you for watching my video. My name is Astrid Krasniqi. In this session today we will be covering a network layer, chapter 6 of CCNA semester 1, Introduction to Networks. This lesson is divided into 4 sections. Section 6.1, Network Layer Protocols. On this section we will explain how network layer protocols and services supports communication across data networks. Then section 6.2, Routing. Explain how routers enable end-to-end connectivity in small to medium-sized business network. Then we will cover 6.3, Routers. Determine the appropriate device to route traffic in small to medium-sized business network. Then we'll finish with section 6.4, Configuring Cisco routers. In my opinion, this is the most fun section because we will learn how to configure a router with a basic configuration. Section 6.1, Network Layer Protocols. Network layer. If we visit again OSI layers, we have layer 7, which is application. Layer 7 deals with what kind of data is it, identify what data is it, like HTTP, SMTP, DNS, and so on. The data is still called just data in this layer. Then we move on to layer 6, which is presentation. Presentation layer deals with formatting, like JPEG, MPEG, and so on. It's still called data in this layer. Then we move on to layer 5, session. Session is like a management of conversation. It's still called the data in this layer. Then we move the packet is going down these layers as for example, we click a hyperlink or something. The packet is the data is going down through these layers, and when it reaches layer 4, transport layer is going to take this data and say, okay, well, I need to segment it. I need to make it into smaller pieces. So it's going to cut it, chop that data in small pieces. So while it's doing the segmenting, it's sequencing them as well. So for example, say that you got a big envelope and that envelope you can't send it. So it's going to segment it into small envelopes, like imagine 10 envelopes. Out of one big envelope, we make it into small 10 envelopes. And then each envelope we will sequence. We will say envelope 1 out of 10, 2 out of 10, 3 out of 10, and so on. And then when we're done with that, we move it. The data goes through to the layer 3, which is a network layer. Now, network layer. The job of the network layer is, now it's called the packet here. The job of the network layer is to identify with an IP address. IP address, source IP address, destination IP address. While it's doing that, now it's called a packet, and it will move it on to the data link layer. Data link layer encapsulates the packet with a MAC address, source, and a destination MAC address, and it will give it to the physical layer. Physical layer is going to put it on the wire. So these are through the OSI layers, going through them again. So the network layer, which is layer 3 here of the OSI, provides the services to allow end devices, like PCs, laptops, and so on, to exchange data across the network. To accomplish this end-to-end transport, so from one laptop to another server somewhere in the other side of the world, the network layer uses 4 basic processes. You need to address the end devices. So PCs, laptops, and every network device needs to have an address. All these addresses have to be unique on the network. You can't have 2 same addresses on the network because you'll get that message, duplicate address found, and so on. So in the same way as the phone has a unique telephone number, end devices must be configured with a unique IP address for identification on the network. Then the network layer does encapsulation as well. In the process called encapsulation, so this is called encapsulation as the packet is going through down the layers, the network layer adds an IP header information, such as source IP address and destination IP address. After header information is added to the PDU, protocol data unit, the PDU is called a packet now. And then we know the routing. The network layer deals with the routing as well. The network layer provides the services to direct a packet to destination host to another network. So from one network, how do I send the packet to a different network somewhere else? And then when it reaches the other side, it deals with de-encapsulation. Like imagine this encapsulation, what it is. Imagine you are sending a friend a really expensive watch. Now that watch, you love it, is best. and you send it to a friend. Now what are you going to do to that watch? You can't just send it to the post office and say, okay, take this watch. So what you're going to do is wrap it, maybe in a bubble wrap, and then you put it in a small box. Maybe if it's a really expensive watch, you're going to bubble wrap it again and put it in another box. That process of adding it to boxes and bubble wrap, that's called encapsulation. That's adding these layers. That's adding to the watch. The watch or the data is right there at the top. But you're going to encapsulate it. You're going to add information to it. So you're going to send it to the other side. And the network layer is like you're writing his address. Your address, the sender's address, and the destination or the friend's address. So we have two very, very important network layer protocols, common network layer protocols that we have current. It's IP version 4, IPv4, and IP version 6, IPv6. Legacy or old, we don't like to say old in the network, we just say legacy network layer protocols. We used to have Novel Inter-Network Packet Exchange or IPX, AppleTalk, Connectionless Network Services or CLNS or DECnet. So the network layer protocols is IPv4 and IPv6. So IP is connectionless. The network layer is not concerned with or even aware of the type of the communication contained inside the packet. IP is connectionless, meaning that no dedicated end-to-end connection is created before data is sent. So with no pre-established end-to-end connection, senders are unaware whether the destination devices are present and functional when sending the packets, nor are they aware if the destination receives the packet, or if they are able to access or read the packet. So it's like when I send a letter to a friend, I'm not gonna like register or guarantee or anything. I'm just gonna send it there. I'm just gonna put it in the post box outside my house, and then hopefully the person I'm sending the letter to will receive the letter. So that's same as IP. I'm not aware if the person is there on the other side, if person is gonna get this letter, or if that person is gonna even be able to read the letter that I'm sending it. So that's why it's connectionless. I don't agree on the timing when I'm going to send a letter. So same, IP is connectionless. Network layer is best effort delivery as well. So IP is often referred to as unreliable or best effort delivery. There is no synchronization, no acknowledgements, no error control, no sequencing. There is no capability for packet retransmission if errors occurs. So it's best effort delivery. So if I send that letter that I sent to my friend, I'm just going to send it to the post box. Now IP takes that letter and is going to do its best to send it to the destination. Most of the time, it does reach the destination, but it's unreliable. If it doesn't reach the destination, I can't complain to anyone or I can't do anything because I just send it in the post box the letter. Same, the IP is just going to send the letter, try and send it to the destination. So they're not going to have synchronization or acknowledgement that they got the letter, or if the letter got lost, I can't send it again because we don't have any acknowledgement, or if there's errors, we can't retransmit the packet. Same time, IP is media independent. It operates independently of the media that carrying of the data at lower layers of the protocol stack. What we're talking in media here is like okay, if I'm sending, if the packet is going through my network is wireless. To get to your network, maybe your network is fiber optic. IP doesn't care. If it's fiber optic in your side, if it's wireless in my side, IP leaves that to the data link there. Data link there is going to deal with what media you're using and what media I'm using. IP is not concerned with that. It is the responsibility of the OSI data link layer to take the IP packet and prepare it for transmission over the communication medium. Now, one thing the IP is concerned with is the media. What media we are using is down to the MTU, because different media will use a different MTU. Then, if you are using different media, IP might fragment the packet, might make it even too smaller. Like similar to transport layer, they segment in the packet. The IP will take a look at the media and say, okay, well, you're using this media and you can't take this big packet, so I'm going to have to fragment them into smaller pieces. Encapsulating IP. IP encapsulates or packages the transport layer segment by adding the IP header. The header is used to deliver the packet to the destination. the IP header remains in place from the time the packet leaves to the network layer of the source host until it arrives at the network layer of the destination host. So like I said, if you, for example, the transport layer is segmenting, it's making these out of one big envelope, the data is coming out from the session, big envelope, and it's segmenting in small 10 envelopes. Each envelope is going to sequence and is going to be handed to the IP. The IP layer is going to add the source and destination for each envelope. And that source and destination address, the IP header is going to add it, it's not going to change. From the source, when it leaves the source, until it reaches the destination, the IP header is never going to change. The source and the destination address. The process of encapsulating data layer by layer enables the service's different layer to develop and scale without affecting other layers. So this is where we have the OSI. So you can have development on different layer, but we don't mess around with the other layers. For example, there could be a new protocol, IPv6. Now maybe there could be another one, IPv, I don't know, something else. We don't have to change anything on the transport layer because transport layer is going to deal with it and is going to hand it over to layer 3. Layer 3, new protocol comes along and it will use the same information. So this is IPv4 packet header. It's divided in two parts. We have the actual IP header, which identifies the packet's characteristics, and then we have the payload. Payload will have the segment, the transport segment, or data, what's inside. So we have to go through what's inside IP packet header. And for your CCNA, as a CCNA candidate, you have to know these fields, what they are. The first field is the easiest one, is the version. It's 4-bit version, identifies what type, what is it? Is it version 4, version 6, and so on. If it's version 4, it will be in the binary. Everything, all this will be in binary. 0, 1, 0, 0. That's a version. And here we move on to differentiated services. Formerly, we are called type of services. Identify the priority of each packet. Okay, all the packets, all the data, everything is not the same. Some of them, they just carry data, like web browsing. Some of them, they carry voice, which they need better priority than web browsing. If you web browsing, if you receive a web page 5 seconds later, you will be okay with it. You will not be complaining. But if you receive a voice communication, you're talking to someone in the phone, and the voice is coming 5 seconds later, that communication is not usable. You're gonna complain. So that's why we have differentiated services. So here we can prioritize. We can say, okay, these are the voice packets. They have to have a better priority. They have to be put in the front of the queue than web browsing packets. Then we have a time to live, which contains 8-bit binary value that's used to limit the lifetime of a packet. Okay, this time to live is like we have a packet. It's gonna reduce one by one. So for example, it starts with 255, and then every hop, every router that it goes, reduces 1. And when it reaches 0, that's it. The packet gets destroyed. It means that we saving the packets from the packets that get lost. They don't go around the world forever. So they're gonna reach a limit. They have a 255 hops limit. When they reach 0, they will be dropped. Then we have a protocol. This is the 8-bit binary value, indicates the data payload type the packet is carrying, which enables the network layer to pass the data to the appropriate upper layer protocols. So in there we can it identifies what is the protocol inside, what data is carrying. For example, the value 1 will mean, okay, inside there's ICMP message, value 6 will mean TCP message, UDP is value 17, and so on. And the two most important things we have here, like we've been talking so far, is source IP address and destination IP address. Then we'll continue with the internet header length. This is internet header length, is how big is this header, the IP header. Then we will continue to the total length. Total length is sometimes referred to whole packet length, which includes this header plus the data, the payload. And then header checksum. The 16-bit field is used to error checking of the IP header. Then, like I said earlier, if, for example, different medium that we are using, the IP might have to fragment the packet. If they fragment the packet, then those three fields here, identification, flag, and fragmentation offset, they will be set. Identification is 16-bit field, uniquely identify the fragment of the original packet. The 3-bit is a flag, identifies how the packet is fragmented, and the fragment offset, the 13-bit field, identifies the order in which to place the packet fragment in the reconstruction of the original unfragmented packet. It's like transport layer segments the packet in sequence, 1 out of 10, 2 out of 10, and so on. So when it gets to the destination will be able to reassemble them. Same is happening here with fragmentation. The IP will fragment the packets into smaller pieces, and then it will kind of like a fragment offset is like sequencing. So the other side will be able to put them in the correct order. Okay, we will see a sample of IPv4 header using the Wireshark and GNS3. On GNS3, I have already configured the router. The PC we'll give an IP address. First, we'll give a IP version 4 address, and then we'll move on to IP version 6 address. Very quickly, I'm just going to check the configuration of the router. If there is no configuration, we will configure very quickly. I'm going to start the secure CRT. Okay. Show, this is small cap, show IP interface brief. Okay, there's no configuration. So what I'm going to do here, I'm going to use, this is fast Ethernet 00. So this side, fast Ethernet 00, you can see on the router, we're going to give it our IP address 192.168.11.1. So open the GNS again, secure CRT. Let me just try and, yeah, there we go. Okay, so configure terminal. I could use config T, but as a CCNA candidate, try and spell all the commands because you learn them, you memorize them better. So it's better learning the shortcuts, but use the long commands because you'll remember them. Okay, we will use interface. For this, I will shorten it. FA00 IP address. What was the address? Yeah. 192.168.11.1 and subnet mask 255.255.255.0, and the last thing is no shutdown. Okay, the configuration is done. So show IP interface brief. Okay, it's up, working. Layer 1 status is up. Layer 2, the protocol is up. So what I'm going to do is I'm going to go to this PCA and give a configuration IP address 192.168.11.100 with that subnet mask, and we're going to ping our gateway as a gateway as well, and we're going to ping it. So for that, I'm using VMware. So I go to start, control panel, then network and internet, network and sharing center, local area connection, open the properties of that, and then internet protocol version 4, IPv4, properties of that. By default, you see it's set to obtain an IP address automatically. Well, we're gonna use a static IP address. So was it 192.168.11.100 and default subnet mask, and as a gateway is going to be our router. So 192.168.11.1. Press OK and close again, close this control panel. Okay, so to start the capture, or to see the IPv4 header, we start the capture. So right click on the green icon here and start capture. This will open Wireshark. Please select the port that you want to capture. I don't want to capture SW1. I want to capture R1 port. and then click OK. So this is our network protocol analyzer, Wireshark, free to download. And then I will go to the host, to client 1 or PC A, and start pinging again my gateway. So ping 192.168.11.1. I'm going to get in some reply. So if I go to Wireshark again, I'll stop the capture and open one of the IPv4 pings. So let me just fix this, put it in correct so we can all see it. Okay. Now here we will see the IPv4 header. So open this field. This is layer 2. This is layer 3. Internet Protocol version 4. Source. We ping in from 192.168.11.100. Destination 192.168.11.1. So if I just scroll here a little bit, we'll see .1. So we can see there's a version 4. The header length, just this header, is 20 bytes. Differentiated services. So you remember quality of services, there's nothing set. Total length, this is actually the length of the packet, the header, including the payload, 60 bytes. Flags, we can see there's no flags being set because this packet is not being fragmented. Time to live, we have 128 here. So every hop is going to reduce 1. So we have 128 hops that this packet is going to go through. The protocol identification, ICMP1. It's there on the inside the payload is ICMP type of packet. Header checksum here for validation is disabled actually. Header checksum. The source address and where is it going? The destination address. Okay, so that's the header inside the IPv4 header. Okay, now we will move on to IPv6 really. So what is the limitation of IPv4? IPv4 has 3 major issues. First, the depletion of IPv4. IPv4 has a limited number of unique public IP addresses available. Although we have approximately 4 billion IPv4 addresses, the increasing number of new IP-enabled devices, always-on connections, and the potential growth of the less developed regions have increased the number of more addresses. Now, in Earth, there's about 7 billion people, and we only have 4 billion IP addresses. Just there, if every person in the world had an IP address, needed an IP address, they can't. There's not enough IPv4. Okay, there's a lot of places they don't need an IP. They don't have access to the network or internet. They don't need an IP address. But each person in the Western world developed world has need for at least, I don't know, 10 IP addresses. So obviously there's no enough IPv4, public IPv4 to address every need. So internet routing table expansion. A routing table is used by routers to make best path determination. As the number of service nodes connected to the internet increases, so does the number of network routes. These IPv4 routes consume a great deal of memory and processing resources on internet routers. And then lack of end-to-end connectivity. Network address translation is a technology commonly implemented with IPv4 network where end-to-end connectivity is lost. Okay, so what is this internet routing table expansion and lack of end-to-end connectivity? Now, with IPv4, the way the addresses that were handed over, there wasn't like a structure saying, okay, well, from 1 to 10, they go into North America, from 11 to 20, they go into South America, and so on. So there's no structure there. There's like number 1, North America, number 2, Europe, number 3, South America, number 4, Africa, and so on. Okay, so the core routers on the internet, they have to have this massive routing table, like 200,000-300,000 routes, and lack of end-to-end connectivity. Now, inside my house, I'm having at least around 10 devices that need an IPv4 address. Now, those devices, they all have a unique IPv4 address, but it's not a public unique IPv4 address. It's a private unique IPv4 address. If I need to go to the internet, to the public network, all my devices will be translated into one public IPv4 address, which is I paid for. So, sorry, I don't need to buy 10 public IPv4 addresses to satisfy all my devices. All my devices have a private IP address, and they will be only translated to public once I need to go to the internet or to access a public network. So there's a term network address translation that's going to translate those private to public addresses. But we have end-to-end connectivity is lost there because there's something in the middle, like a man in the middle, which is, okay, fine, now I want that man in the middle, like my router, to change the IP address. But there's no end-to-end connectivity. So for that reason, we have improvement that IPv6 will provide towards from IPv4. First, you could tell that it's a lot smaller table, so less field on IPv6. So IPv6 will provide a lot more addresses because it's using 128 bits instead of IPv4 is using only 32 bits. So 32 bits gives you 4 billion, around 4 billion. 33-bit gives you 8 billion. So every bit you just double in the size. So we're talking about 340 decillion addresses with IPv6, which is roughly equivalent, it says, to every grain of sand on Earth. So you can imagine how many IPv6 addresses we have. So improved packet handling, IPv6 header has a simplified with a fewer fields, like we can see it up here, a lot less field than IPv4. We don't need IPv4 for IPv6 because we have so many IP addresses that all devices will be able to get a public IP address. And the security is integrated. IPv6 natively supports authentication and privacy capabilities. So what's on these fields? On those fields, the first one is version. Now version, same as IPv4. It has, this time it says 0110, which in binary, if you convert it in decimal, it means 6, version 6. Traffic class is same as an IPv4. The name has changed. Now it's same as differentiated services. It's just priority of the packets, which has better priority, which has less priority. Flow label is new. This 20-bit field provides a special services to the real-time application. It can be used to inform routers and switches to maintain the same path for the packet flow, so the packets are not reordered. Payload length. Payload length is the total length of the same as total length in IPv4. It defines the entire packet, including the header and the optional extensions. Next header is same as the protocol field on IPv4. It just identifies what payload is it. Is it ICMP? Is it TCP, UDP, or so on? And the hop limit. This is the hop limit is TTL, same as TTL field on IPv4, 8-bit fields. Hop limit is how many hops the packet is allowed to go through. So imagine, again, maximum is 255 hops. Every hop from router to router is 1 hop. So at every hop, the router will reduce 1 of this hop field. For example, from my router, my home router to my ISP, that's 1 hop. From ISP to another ISP, there's another hop. So each router, as it goes through, each router that the packet goes through is counted as 1 hop. Okay, now I'll show you a demonstration on viewing IPv6 header using Wireshark on GNS3. Again, same network as we had earlier, so similar network, or same network as we had with IPv4 header. So this time we're just going to give an IP address, IPv6 address for this router and this PC, and then we're going to use the Wireshark again to check the IPv6 header. Okay, so if I get my CRT, so first thing, to give an IPv6 address, I have to go to config or configure terminal. I will have to enable IPv6 unicast routing because by default unicast routing for IPv6 is not enabled. So IPv6 unicast routing. Okay, and then I have to go to that same interface, which is FA00, and give an IPv6 address. So interface FA00 IPv6 address and 2001 db8:1/64. As you can see, the address is there. Yeah. Okay. I don't need to do no shutdown because I've done it for IPv4, so none of that. Show IPv6 interface brief, and we can see that 2001 db8:1 is there. Okay, so now I need to go to this client machine and give an IPv6 address as well, static IPv6 address, and ping it, and so we can see the header. So I'm going to open my client machine. It's here. Again, open the control panel. So start control panel. cancel this. This is just a practice PC. So network and internet, network and sharing center, local area connection, and then properties of that. Now I'm gonna select version 6 properties, and I'm gonna use the following. So I'm gonna use a static, not dynamic. So I'm gonna use 2001 DB8 : I don't know, A 64-bit, and the gateway is 2001 DB8 : 1. That's my gateway. So click OK, close, and oh no, don't cancel that. Cancel that. Close this. Okay, so I'm gonna go back to my GNS and right click on the link here. Stop the previous capture. I'm gonna start a new capture. Yep, not the switch, the router. Click OK. So this will start again the Wireshark Network Protocol Analyzer. And what we're looking is IPv6 header. So, okay, we got already some, but network solicitation, network advertisement, and so on. But I'm going to go to my client machine and start pinging it. Let's ping IPv6. So, ping 2001 DB8 : 1. I got some reply, and I got some requests and replies there. Okay, so stop this, and I'm going to open one of the headers. So I'm going to rearrange it so we can see it. Come on. There. Okay. Here, open the IPv6 header, and we can see it's a version 6. Payload length. That's a header and a payload. Next header, so you can see the ICMPv6 code 58. Next sublimit 128. Then we have a source and destination header address. So as we can see here, it's like this is the IPv6 header. We can see it on the Wireshark. Close this. I don't need this anymore, so I can close it as well. And no, quit without saving. Okay, so we saw IPv6 header and IPv4 header. See you on section 6.2, routing. Bye.